All right. Hi, everyone, and welcome. Welcome to our ARM AI Tech Talk series. This is the place for the latest in AI from trends, technologies, and best practices from ARM and our ecosystem partners. And it's great to have you here today, wherever you're joining us from in the world. We are really excited, and I'm personally really excited today by today's Tech Talk. I'm hoping lots of you would have seen what is arguably the best promo video for any Tech Talk we've ever done. I'm completely unbiased, of course, to any of our ecosystem partners that have done Tech Talks, but I'd like to give a special shout out to the team behind a fantastic promo video for today's Tech Talk. This has been a topic I've been looking forward to for some time, and a talk I've been looking forward to for some time. And I'm super excited and honored to have Emza and Alif joining us today for what is going to be a fantastic talk, all featuring the Cortex M55, Ethos-U55 running on Alif Silicon, featuring a fantastic demo from the Emza team, one of our AI ecosystem partners. Now, before I get started with the talk, just got a couple of little housekeeping items because I'm sure we want to get straight to the demo, right? But just got a couple of little things I want to go through. So, Eitan, do you mind flicking to the next slide? Just because I want to share with people how they can get in touch with us and how they can get involved in the conversation. So if you like what you see, want to get in touch, please do tweet us at ARM Software Dev. Use the hashtag AIVTT. We'd love to hear where you're joining us from and how much you've enjoyed today's talk. And hopefully the demo has inspired you to think about all kinds of things AI and ML. These tech talks have been going for quite a couple of years now. We've got about 40 or so done. And there's a YouTube channel which has all of these. Our YouTube channel playlist has all of these available for you to go and watch on demand. This talk is also being live streamed to YouTube. So a special shout out and hello to all folks joining us on YouTube as well. And of course, this is not just a one-off and not just ones we've done in the past. We've got a bunch more coming up. So you can sign up for those. Just go to arm.com/tech talks to sign up. And if you want a sneak peek at what those are, let's just have a look at the next slide, Eitan, if that's all right. We've got another 3 scheduled straight after this, and actually a 4th we're just working on for July before we take a little summer break. So we're going to be talking we're going to have a panel session in 2 weeks from Plumerai, DeepLight, and Revero, talking about computer vision on the edge. That's going to be really interesting. We haven't done a panel session for a while, so do check that out and register for that if you're interested. We've then got Edge Impulse talking about running object detection on ARM Cortex M7. And we then got 2 weeks after that, Nota AI talking about hardware approach for neural networks. And that's on U65, actually, our other micro NPU. But let's get to today's topic, right? Today is all about the ARM Ethos-U55 Cortex M55. And it's my great pleasure and honor to introduce Henrik and Eitan. Do you want to just flick to the next slide so we can see you on camera? I can see you. Here's some profile pictures of yourselves. And it's great to have you guys here today. For all the audience, I'm about to go off mute and off camera, but if you guys have any questions at all during the tech talk and you're joining us on Zoom, then please just use the Q&A function just down there on the Zoom menu bar to ask any questions as they come to mind. We've got plenty of time for questions after today's talk. And if you're on YouTube joining us, then just head over to the Zoom link I've pasted if you've got a question and want to ask our presenters about this. So Henrik, Eitan, and team from Emza and Alif, it's a great pleasure to have you today. It's great to have you. And enough from me. Let's hear this demo. So Henrik, Eitan, over to you.
Thank you so much, Tobias. I'm going to kick this presentation off by just going through a bit of background on Alif as a company and also talk a little bit about the device that is going to be used in this demo, our Ensemble E3 device that is outfitted with the Cortex M55 cores and the Ethos-U55 micro NPU. So Eitan, if you could switch over to the next slide. We got the agenda slide up here, so you can kind of see how we will go through the presentation. I'll do the intro to Alif and Ethos and talk a little bit about that. And then Eitan is going to go through the architecture of the model used, the data sets, how they were being put together and trained with the parameters, results, model conversions, deployment, and summarize the results. So could you switch to the next slide, please? So about Alif Semiconductor, if you haven't heard about us before, we do make devices intelligent. That is what we have set out to do. We are a silicon startup. It's kind of rare for a company like us to be kind of in a startup phase. We were founded in January of 2019, and we've already been able to spin out a couple of revisions of our Ensemble family of devices to the market, featuring the M55 and the Ethos-U55, as I mentioned. Company is global. Ensemble. The team is based in US, India, and Singapore. And what we are doing, what we're trying to achieve with our devices is to pack in as much functions and features as possible on a single monolithic die to essentially create an IoT system on a chip type solution. We include scalable processing features, very battery friendly operation. We've architected all of our devices to be as power efficient as possible from the ground up. Very strong security features, and also, of course, enabling edge AI features. We are the first silicon in the market with the Ethos-U55 micro MPU, and we actually include 2 of these micro MPUs in our solution, and I'll tell you why we do that in a little bit. Can you switch to the next slide? So this is the overview of our Ensemble product family from the top, how they scale from a single core device that's a single M55 and scales up to dual core, triple core, and a quad core setup. The 2 smaller devices, the E1 and the E3, are microcontroller oriented. They contain MCU cores. And as we scale up to the E5 and the E7, we enter into what we call fusion processor territory, where we also add MPU cores for running high-level operating systems in addition to the low-level kind of control cores in the E1 and the E3 devices. Can you switch to the next slide? This is how that looks like if you look at what is actually inside the devices. So in an E1 device, there's a single M55 and a single Ethos-U55 unit. In the E3, there are 2 M55 cores. One is configured for high efficiency, meaning it uses very, very little power, and one is configured for high performance, running up to 400 megahertz. And they each have their own Ethos-U55 units paired up with them to do machine learning operations. And then in the triple and the quad core configuration, we also add Cortex A32 cores, a single A32 in the E5 and 2 Cortex A32s in an SMP configuration, running out of the same level 2 cache for maximum performance on the higher end side of things. You can switch to the next slide, please. So the reason that we include 2 Ethos-U55 units in our system is we wanted to be able to create an AI-powered environment sniffing engine that was designed for low power operation and for ultimate flexibility. So what we've done, if you look in the blue box on the diagram on the screen, that's where we have our high efficiency system. This is configured for the lowest possible power consumption while it's active. And since we have a dedicated Cortex M55 unit in that system with dedicated memory also in the low power region, we can essentially have this always on sniffing engine operating using machine learning to sense the environment around the device and to try to detect if something is going on that the device should be aware of, and run classification continuously. When this high efficiency system discovers that an event is taking place, it can wake up the high performance subsystem, which has the high performance M55 running at 400 megahertz and an even wider Ethos-U55 unit that can go in and classify the event in a lot more detail to really establish what happened to cause the trigger to trip. Is this an event that I have to take an action on, or do I just report back, that it was this particular person that walked past the camera, or whatever the event might have been. We also have configured the system to be very flexible in regards to how you can actually run your AI models in this system. So between these two subsystems, the high efficiency and the high performance, you can essentially share any system resource, any memories, any peripherals. You can map them to the proper system to make sure that the model has the ability to execute exactly the way that you want to. So that's just a short overview of Alif's system in the Ensemble devices and how we've set it up. Go to the next slide, please. This is available now. We have been sampling our devices to the market for the better part of a year. The entire range, the E7, the E5, the E3, and the E1 is available on evaluation boards. This is the same evaluation board, by the way, that will be used in the demo that you will see. And you've got some links up on the screen here, alifsemi.com or contact@alifsemi.com if you're interested in getting your hands on one of these boards and exploring the Ensemble devices further. Thank you for giving me the opportunity to introduce Alif and the Ensemble devices. I'm going to hand it over to Eitan now to take you through the demo.
So, hi everyone, I'm Eitan, the tech lead from Emza. So a few words about Emza. So Emza is a pioneer in tiny edge AI-based vision solution since 2016, enabling mass market deployment with optimized power, size, and cost. We have actually now the WiseEye ultra low power vision solution is shipping with the laptops, and we are partnered with ARM for future collaboration. So I'm really excited to share with you the first silicon with the new and promising architecture of the Cortex M55 and Ethos-U55 micro NPU. We want to take you through a journey from selecting a model, modifying to the specific application needs, training, and evaluating it. After we have the trained model, we want to test it without the reliance on the real hardware. So for this step, we have the fixed virtual platform, enable us to run the application on the PC and get a good estimation about the performance on the real hardware. This step ensures the correctness of the application and proceed the risk to early stage of the development process. And of course, finally, the highlight of this talk will be the live demo. So there are many use cases for object detection. We choose to demonstrate face detection with additional facial information with a detection distance up to 2 meters. The facial information includes the pose of the head, specifically the yaw angle, which gives us a pretty good estimation if the detected face is looking at the camera. In addition, we detect 5 facial landmarks: the left and right eye, the nose, and the left and right side of the mouth. Those facial landmarks enable us to have a better understanding about the detected face. For example, it can be a first stage before face recognition for alignment. If you know the eyes, you can know where the ears, so you can use it for audio beaming or distance between the eyes to estimate the distance of the detected face from the camera. So there are also other potential use cases like user presence and contact awareness for smart devices, and also human detection for home security, doorbells, smart TVs, smart cameras, and the like. So we just want to focus on one application. So let's talk about the model architecture. So the pace of new models is overwhelming. And for this demo, we decided to show the most common detector architecture, which rely on the seminal paper from 2016, known as SSD, single shot multi-box detector by Wei Liu and others. For the baseline model, we choose one of the many applications from the open source, and we modify it to our specific application needs. The original image was RGB, so we decided to train it on a grayscale to decrease the memory requirements, as memory is one of the most expensive hardware components. And for our application, we need to add additional detection heads for the yaw and the landmarks. So the model gets image 120 by 160 grayscale image, pass it through the backbone, and we have 4 heads, one for the face classification, one for the regression where the face is located, one is for the yaw angle of the face, and the last one is for the facial landmarks. So now let's go a little bit in depth about the model. So the model can be divided into 2 parts: the backbone, which is responsible for the feature extraction, and the heads, which is responsible for the detection. The backbone comprises of 15 blocks. Each block comprises of different combination of convolution, activation, and batch normalization. For example, you can see the brown and the green block implement depth-wise separable convolution as introduced in the MobileNet paper. In this example, the kernel size is 3 by 3, which gives us up to 9 times less computation than the regular convolutions. to enable the model to detect objects in different sizes, feature maps from different parts of the backbone used as input to the detected heads. So if I show you this, so you can see we take the feature map after the 8, the 11, the 13, and the last layer. Those 4 feature maps get into the regression and then the classification head. And for example, you can see here the feature map 4x5. We have 20 locations. In each location, we choose, in this example, 3 anchors to regress to. So if you do the calculation, you get a total of 1,118 detection in each forward pass. So this number is chosen by design. And just for a reference, the original SSD paper used the input image 300 by 300, the RGB image with 6 feature maps, with total of 8,732 detection per class. So this is quite a small model. It's small model, but it's not that small. Regarding the data sets. So for training, we use 3 public data sets. We use wider Yale and Celeb A. And we had additional Emza proprietary data set, which is actually a subset of a larger data set we collected here at Emza over the years, with emphasis on the specific scene and grayscale low resolution images that are common to the sensor that we are used to work with. We re-annotate them using the state-of-the-art models. Retina face was used to extract the class label, the bounding box, and the facial landmarks. And when it was used to extract the face pose, all pitch and yaw. In this application, we choose to focus only on the yaw angle. So we just use the yaw, and the final step is to convert all images to grayscale, because we want to train only on grayscale images. The total number of images before augmentation is about 80K, sorry. Now for the training parameters. So we train in Python using the PyTorch library. So there are a lot of examples showing promising results using transfer learning for using pre-trained models as a backbone, train on images on millions of images. We couldn't use them because we train on grayscale, because we want to train on grayscale. So we need to train from scratch. And also some papers suggest that training from scratch on the right data, meaning the right scene and image quality, gives same or even better result with much less images. Regarding the input resolution, we use 120 by 160 by 1. This is of course a compromise the distance versus memory. For the up to 2 meters, this is more than enough. Regarding the dataset, we'll show later in the next the results, but we choose it's important to choose the relevant scene for the application, and also the image quality as the image sensor that is used in the application. Augmentation, we use the regular photometric and geometric ones, and the loss function for the classification was the cross entropy, and the regression was the smooth L1, which is a combination of L1 and L2, which is more robust to outliers. Some results. So on the upper left side, you can see the true positive rate versus the false positive per image on the COCO dataset on the person class. On the upper right side, some detected examples. The red numbers is the yaw angle in degrees. On the bottom left side, you can see the validation training loss. The light yellow is when we train on the public dataset, and if we add the Emza dataset, you can see that the loss is getting smaller early in the training stage. So adding specific data for the application, making the training much better. On the right side, on the bottom right side, you can see some result on Celeb A. The landmarks normalized mean error, and the yaw mean absolute error, and some examples of detections. Now, after training the model in PyTorch, the training output is a set of weights in a PTH file. Then we need to construct the model using TensorFlow and load the train weights from the PTH file to TensorFlow. There is an issue between PyTorch and TensorFlow. You need to switch the channels when you load the weights. Then we we use the TensorFlow converter. We convert the model to TensorFlow Lite Micro and we quantize the operators and the input and output to 8-bit integer. The end component is a TF Lite file of the model. And next we need to do the build process to run the model either on the FVP or the real hardware, which we'll go through in the next slide. So now we have the TF Lite model. It's a TFLM model. Now we want to run it on the FVP. We need first to pass it through the ARM Vela compiler. The ARM Vela compiler convert the operations that can be run either on the Ethos or on the Cortex. And if the operation is not supported by the Ethos, it will be then the Cortex M have two options. You can use the CMSysNN, which is optimized for low-level kernels for Cortex M CPUs. And if this is also not supported, then there's the reference kernel from TFLM. After the Vela compiler convert the model, you have the output log. You can see first we configure it to the right number of, you can choose, there is different flavors for the Ethos. You can choose the number of Mach per cycle. Here we choose the 256, as this is the same as the one on the hardware, the demo board that we will demonstrate later. And also the clock is 400 megahertz. And here you can see the total SRAM used. This is the Tensor Arena. This is the SRAM used in runtime and the model size on the flash. The third important parameter is the operation, which operation run where. Here you can see that all of the operation will run on the micro NPU, which is the most efficient. Then you have the number of cycles and the inference time. So to have the FVP development project, you need to clone the repo from ARM. You have the link here and in the end of the slides. You need to clone Emza repo. It's public on GitHub, and merge them, and then you can build and run the FVP. The fixed virtual platform are complete simulation of the ARM system, including processor memory and the peripherals, and which gives a comprehensive model on which to build and test your software. And now we'll see a demo of the FVP. Okay, so now we'll run the FVP. Okay, so this is the Corestone 300. It's a subsystem that mimics the hardware. And on the right side, I have the terminal that sends commands to it. And now I can run an image to make inference. So the running is taking about 10 seconds. This is because it's emulating in software. And there you can see you have the detection. You have the red boxes with the detected faces, the landmarks, and on the right side you can see the detected yaw angles. Let's see another image. Okay, and Here you can see the expected face. So now that we are happy with the results on the FVP, we can continue and deploy it on the real hardware. Switch back to the presentation. Okay, after running the application on the FVP, we want to deploy it on the target board. So the main part of the application, mainly the algorithmic pipeline, doesn't need any changes. The only thing that changed is the input. Now it's a live camera stream instead of the still images we used in the FVP. And the output is now is a LCD display. To deploy it on the Alif evaluation board, you need to clone Alif repo. For this, you need to contact Alif, and you need to clone Emza repo. It's public on GitHub. You need to merge them, build, then you can deploy it. On the right side, you can see the tree of the project. The only thing that changed from the FVP is this orange folder with the Ensemble, which is the BSP by Alif. Okay, now we can go for the live demo. So this is on the left side, you can see the evaluation board. Okay, this is the camera, and this is the Alif main board. And on the back side, you have the LCD screen. And now we can switch to the demo. Okay, so here you can see Tomer. Hi, Tomer. It's sitting in front of the demo. It's running now in real time and detecting it and seeing the result on the LCD. I know we cannot see it really clear, so now we just want to show you the scene. And now we'll switch to the zoom in camera, looking straight on the LCD. Okay, here is the other camera. The artifact is due to the LCD of the cameras, not related to the algo in any way. Okay, so here you can see Tomer with the detected red bounding box and the 5 facial landmarks. If you can do some, you see, if you move the head, you can see the magenta bar underneath the box. It's the yaw angle in degrees. And you can go back and the distance, okay. This is about 1.5 meters. And we can try maybe more people. Okay, it's good. Okay. It's half of the company in English. Well, and now we will go back to the presentation. Okay, so we didn't put the FPS on the board, but we tested beforehand. So now for the important numbers. As you can see, the speed up using the Ethos-U55 micro NPU is very impressive. You have the high efficiency and the high performance configuration. In both of them, it's almost 2 orders of magnitude. The demo was on the high performance. So to conclude, we saw how to choose a model from the open source, modify it to our application needs, run it on the FVP, and finally deploy it on the real hardware. The FVP by ARM enables fast development without the constraint of silicon availability. The improved inference speed, almost 2 orders of magnitude, opens the door to much more complex models and vision pipelines in cost-effective fashion. We believe this improvement will ignite the market of edge computing and will see a rapid increase in products in this segment in the near future. Here are all the resources, the model that we use from the open source, the models that we use for the annotation, the ARM repo, our repos, and our website. And first, I just want a few words. I want to say thank you to Alif for the fast and professional collaboration, and I want to thank ARM for the opportunity. And lastly, I want to thank my team, Michael, Elad, and Tomer, for the effort and the teamwork. It's always a pleasure to work with you guys. Thank you.
Awesome. That was amazing. Thank you so much, Eitan. And thank you for a fantastic cameo from half of Emza to doing face detection live in a demo. You know, when we conceived these products years ago, it's, you know, we think of all the great use cases and ideas that our ecosystem partners and silicon partners and others will come up with and deploy live. And it's just awesome to see it working live on such a small bit of silicon and with such incredible performance, right? Real-time face detection from you guys, just awesome. And thank you for running through how you guys got there. We, of course, as I mentioned in the chat, please get your questions in. I'm sure there's a bunch of questions out there for Emza and for Alif. I can take a couple that are on there right now. One of which is from Lee Shung, and apologies if I've any for mispronunciations of names during this Q&A section. Wondering what the FVP is. This is a fixed virtual platform, so it's a virtual representation of a physical board. And actually, just 3 weeks ago now, apologies, we launched an expansion to our ARM virtual hardware offering. So I'm going to paste the link in the chat. So everything, including this reference board, the Cortex 300 that Eitan and team got going on the FVP before they then deployed onto the Alif Silicon. That is all available in ARM virtual hardware today. You can go and sign up here. I'll post a link in the chat very shortly. So all those capabilities and more across the whole range of reference boards and partner boards are all available on the ARM virtual hardware website. So I'm going to put that link in the chat very shortly. I think we've had a couple of questions on this, and for Henrik actually, and one of the questions I obviously would have as well is, when's this going to be available, Henrik? When's when's Alif's, you know, is the dev board already available for buying, and then when's actually going to be generally available?
Yeah, so the dev board is available for purchase right now. We've been sampling, I think I mentioned that during my part of the presentation, we have been sampling the Ensemble devices for just about a year now. To lead customers. So we have the devices, we have the boards in particular. We have started to partner with Arrow as a distributor, and Arrow is able to facilitate orders for our boards. We do require that you contact us first because we have an NDA requirement before we release the pre-mass production silicon to customers, but it's a very smooth process. So just send an email to contact@alifsemi.com and we'll get back to you with details on how to order boards and samples and things like that. And for mass production quantities, we do expect Ensemble to be available through traditional distribution channels before the end of this year. So that's our target.
Brilliant. Thank you, Henrik. I'm just posting a link for more information about ARM virtual hardware in the chat, so anyone interested. And in fact, talking about links and contact info in general, a copy of these slides together with the recording will be live very shortly afterwards. Recording goes live straight away because it's live streamed to YouTube, and we hope to get the slides from today, which have all the links and all the contact info on our developer.arm.com/tech talk website, which has all the documents from and all the slides from prior talks on there. Should be live hopefully in 24 hours, I reckon. Also, you'll get a follow-up email by the end of this week where you will be invited to check it out. So it will definitely be up by then. So thank you for that. And actually, I was going to ask a question for the Emza team, kind of a two-part question, was, you know, how many faces can you detect in one scene?
Well, the number of faces is constrained by the number of feature map and anchor boxes. If you recall from the architecture slide, the limit in this architecture is 1,118 faces.
So we need a bigger company to really push it to the limit. So let's get you guys some more employees. And actually follow on from that, does the inference time increase with the number of faces that you detect?
Well, no, it's also it's the nature of this architecture. The number of detection, the speed is always constant, no matter how many people are in the frame, unless you pass the 1118 limit, of course.
Gotcha. Thank you for that. And let's jump to another question. So let's go to George Gekov. Thanks for a great talk. No problem, George. Thank you for joining. 4 milliseconds per inference means you're able to achieve around 250 FPS. What are the computer vision use cases requiring such a high FPS?
Yeah, I can kind of talk a little bit from Alif's perspective, and I'm sure that the Emza team can also fill in on this. I'm not really sure about 250 frames per second if that particular number unlocks specific use cases, but kind of what we're going for when we have designed the Ensemble devices is to have enough performance in there to cover a wide range of image resolutions, because the inference time will scale somewhat linearly to the size of the image that you're going to run these inference operations on. So for this specific demo, there's a certain image resolution that is being used, and that's going to affect the time it takes to do the inferencing. So I don't know, Emza team, do you have any additional comments here on use cases and frames per second, and kind of what is the sweet spot for the majority of the use cases you see?
Well, this is just a small example. Of course, you can take a much more complex model. This is just to give you a estimation about the performance that you can achieve. But also, if you use small models, you can use cascade of models for different tasks, one after another, and you have more time to do other vision tasks or other pipeline tasks that take more time.
Thank you both. That's great. What's the top focus question at the moment? And do, in addition, folks, if you're looking at questions you think, oh, I'd like that one on top, then just do give it a thumbs up in the Q&A box. What's the benefit of using PyTorch to do the model training rather than using TensorFlow, especially if the model is eventually converted into TensorFlow Lite for deployment?
It's mainly a choice of preference. We prefer to train. It's more flexible to use PyTorch. Most of the development today is using PyTorch, but you can also do it in TensorFlow.
Thank you. Actually, on the topic of TensorFlow Lite Micro, if and when will TensorFlow Lite Micro support the demo board?
It is supported already. So the tooling is there for working with TensorFlow Lite Micro output, and we have examples on how to do that available for the board.
Amazing. Thank you. Thank you. That's great to hear. Can you then, just a question actually, do you mind if I'm going back to the slide with the performance uplift? You showed about 80 and 90x improvement, but they didn't quite see what you were comparing between. So I think it's between M55 and, yeah.
Yeah, okay. So on the left side, you can see first the high efficiency configuration of the hardware. So we're comparing using only the M55 or the M55 with the micro NPU, the Ethos-U55. On the left side, on the right side, it's the same comparison, but in the high performance configuration of the board.
That's a great comparison, and thank you for, it's a great question as well, and good to show. Anton's then asked, thanks for the presentation and the demo. Were any weight compression techniques such as pruning, weight clustering, etc., applied to the model? And if so, I guess could you go into a bit more detail about what you did for the compression techniques? If so,
for intake.
I believe so. Yeah, just were any weight compression techniques applied to the model?
No.
No. Gotcha. Fantastic. I mean, in terms of another question I had, and do folks keep your questions coming in. looking at the model itself, I think going a bit more on the model, what other attributes or what other data could you extract from the image? I guess people are talking about, well, in the past, given that COVID has been around for a couple of years now, things like, face masks or something. Is that something you could pick up from the image using this model?
Actually, yes. I just go back to the slide. So here you see, we take the baseline model was just the classification and the regression for the bounding box. We added the yaw estimation and the landmark head. So you can add additional heads. The only issue is that you need to annotate the data for the training. But if you have the annotation, let's say the masks, then you can do another classification head for the mask, no mask.
Amazing. Yeah, thank you for that. That's great. George has then asked for yourself, Henrik, I believe, will your devices interface with Edge Impulse?
Yes, so they will. We actually just, when did we do that? We did that last week on Thursday. We published a press release announcing full support for our Ensemble devices in Edge Impulse's development environment. And if you're around in the Bay Area, we're actually showcasing this at the Embedded Vision Summit that starts today at the Expo. There will be demos in Edge Impulse's booth there of their tools running together with our Ensemble devices.
Absolutely, yeah. And if you're in the area, do head over and check it out. I think quite a few folks from ARM are also over there, so I'm sure you can catch quite a few people over there. So do keep an eye out for us all. We've then got another question just come in. Did you try object detection on the live video camera? What model algorithm did you use? So I guess in terms of rather than face detection, object detection specifically.
What other than face detection? Other than face detection,
I think, and Ram, please do comment or add another question just in case I misinterpreted, but I guess they're referring to more broader object detection here.
We do human detection, and yeah, that's about it. Face and human mostly. And in the past we did some leg detection for detecting the position of the legs for some gesture recognition for the automotive industry.
We've also run some models. We had some demos using models like MobileNet V2 and things like that to classify objects and to perform those kind of functions. So it's definitely doable. It's Ethos as an accelerator is very general purpose oriented. It's not targeting specific use cases.
Absolutely. Question on the and actually, just before I jump to the questions, I think Serge has asked in the chat, hands and finger detection, would something like that be possible?
We can, but we didn't have the opportunity to do it until now. But it's not an issue. The classification, the object. It's just we need the data, the label data.
Exactly. Question on the model from a computer vision newcomer. Why do you want to detect the face yaw angle?
So we want to, it's for application where you want to understand where is the face the user is looking. Let's say for laptops, if you want to see if the person is looking at the screen, and if he's not looking at the screen, you can do stuff like dimming the screen, lock it, or have some awareness of get some contact awareness about the user.
Brilliant, thank you. And the around 100x performance improvement that was achieved that you mentioned at the end, was that achieved by hardware only, or was there any software optimization involved going from M55 to M55 plus U55?
I can kind of talk.
Pure hardware.
Well, it is mainly done by hardware, but there's a lot of parts of the hardware architecture in our silicon that plays into this. one of the key things really is about how the memories in the system is organized to be able to essentially feed data to the M55 unit and the Ethos unit in a way where it doesn't necessarily, stall that inference pipeline. So that's one of the things that we worked really hard on trying to optimize and make flexible in our system. So you'll definitely see some part of that performance coming from there, but then also Ethos is, it is really good at accelerating, CNN and RNN type models.
Amazing. Thank you for that. Just to recap, I think, Etienne, you might have spoken about this on a previous slide in the talk. What's the size of the model that was being used?
So for the training in Python, it was 1.3 megabyte, but after quantization, it's around 0.4 megabyte, 440 kilo.
Brilliant. Thank you for that. We just had a question actually in the chat, which I'll very quickly ask. What's the size of the TensorFlow-like micro arena?
384 kilobyte.
Fantastic. Then Marconi's asked, will the device support speech recognition, keyword spotting applications, and what hardware audio interfaces does it support?
Yes, it will. We actually have a demo, a keyword spotting demo that is also using the Ethos unit for our board. We have I2S microphones on the eval board, and we also have PDM interfaces in the device, so you can capture audio from both analog and digital microphone sources.
Brilliant. Thank you for that. How many objects do you reckon you could detect with MobileNet SSD-like models while keeping the model light in terms of memory footprint?
It's more than you can see. If you're looking for 2 meters, more than you can fit in the image. Like on the more than 10, more than 20. It's not the number of detection it's not a problem. It's not a limitation.
Thank you for that. And then the next question I can partly answer, but folks on the call, if they want to jump in. What happens if the operators aren't supported by the Ethos cores or the Cortex-M? So in terms of the software stack, if they're not supported by Ethos-U and directly operated in the Ethos-U, they will fall back to the Cortex-M and either be run by, SimSysN or the TensorFlow-like reference kernels and TensorFlow-like reference operators. So I don't know, Henrik, have you got anything further on that to?
No, I mean, that's correct. I don't think that there would be a situation where an operator would just not be supported because, like you say, the reference kernels will just defer that operation to the microcontroller, and it will be able to run the operation, albeit without the level of acceleration that you would get from being able to schedule it on the Ethos. So it would run slightly slower, but it will still run.
Yeah, exactly. There shouldn't be that case. It should either run Ethos-U or Cortex-M, just in terms of different acceleration paths. So, we've had lots of questions, absolutely lots of questions come in. Is the evaluation board available for home use, as someone has asked?
Well, once you have it, we don't limit where you use it. So
no trackers or anything.
No, exactly. So yeah, you could absolutely use it at home.
Thank you for that. And do keep your questions coming. We've still got a good 5 minutes or so and be happy to answer any questions. There's been a fantastic lot. I've loved the variety of questions that's come in is great. It's really engaged the audience, this demo. Marconi's just asked, do you plan to work with Adafruit, SparkFun, or Seed Studio for a smaller form factor development board?
Yeah, that is an interesting question. We are actually in the process of doing a design revision of the board, where we will take the current board, which is kind of generic in its design. We haven't really targeted a particular use case for it because our devices at the core is, microcontroller devices. They're suitable for a lot of different applications, but we're doing dedicated boards specifically for AI type use cases where we are, optimizing size. We're making sure that we have all of the necessary features and interface modules to be able to capture data to perform machine learning algorithms on, integrated on the board. So that's an ongoing effort. We plan on being ready with that and having those boards in the market at the time where we open up for general high volume production type orders when the devices are fully qualified before the end of the year. So expect to see some boards in that regard. Who exactly we're going to partner with for making them available, that's still something that we're looking into.
Brilliant. Thank you, Henrik. Can Emza envision a model that could split the inference between the high performance and high efficiency subsystems running in parallel?
You can do what come to my mind is to do a vision and an audio in parallel, but it's application requirements. So depending on the application, you can do recognition and detection in parallel, but it's really depending on the requirements of the application.
Yeah. Brilliant. No, thank you for that. And Henrik, flicking back to you, why did you choose what you did for the high efficiency clock speeds?
So the clock speed for the high efficiency subsystem that's kind of the maximum clock speed for it. You can of course run it at a slower clock rate if you don't need to run it that fast. The reason that we went for that range is we wanted to make sure that even if you are running a part of an application that needs to be low power and kind of power conscious, that we still have enough performance in the device, in that subsystem, to be able to execute that efficiently, right? Because you want to be able to finish the workload fast so you can go to sleep sooner. That's how you save the most amount of power. So that's kind of what we were targeting. And there's a lot of architecture details, about how the clock trees are structured and very like in-depth technical explanations for some things in there as well. But really, we kind of looked at what are the benchmark clock speeds for highly efficient devices today, and what should they be when you add machine learning into the mix, so that you can execute those type of workloads at an efficient rate.
Brilliant. Thank you, Henrik. And I guess the final question before before we wrap up is, what is the factor that increases the SRAM usage of the model, the tensor arena, if it isn't the number of detected objects? I thought that the more objects you detect, the larger the SRAM memory footprint of the model that it is.
Well, of course it's the number of layers, but the main contributor is the input resolution.
Brilliant, thank you. And I'm going to be, as Pete, for those folks who have stayed through the Q&A, and there's a hell of a lot of you, I'm going to give you guys a special treat. If Emza, if you're okay with it, can we see the demo one more time? Let's see the demo one more time. I think it's super cool. I think as people have stayed to the end and gone through loads of great questions from the audience, let's show this demo off one more time. Face detection live, running on the Alif Silicon Cortex M55 and Ethos-U55. Let me spotlight. Fantastic, we can see you. Go on, let's get everyone in.
Want everyone in?
Go on, let's get everyone in. If we can, if they're still there. I hope they're still there.
Yeah.
It's an awesome job from the whole team. So it's great to have you guys detected on the Alif board. Isn't that awesome? Seeing this live working is just fantastic. There's even one hiding.
Okay.
Amazing. Thank you guys ever so much. Emza and Alif, you guys have been absolutely awesome. A great demo, really interesting tech talk that's walked us through, a whole bunch of material. And I hope everyone in the audience has loved it. We really, really appreciate everyone's time, taking out their time to watch this tech talk today and joining us for another AI Tech Talk series. And if you like what you see, you'll be redirected to our arm.com page to register for our next Tech Talk, a panel session on computer vision. And you'll also have a chance to register for all our upcoming Tech Talks right through to June that are currently scheduled. So if you like what you see and you want the latest for AI trends, technologies, and best practices from ARM and our ecosystem, then this is the place to be. You'll be able to watch everything. If you've missed any part of today, if you have to drop out for any reason, you'll be able to watch the recording straight away on YouTube. It'll be live straight after we finish today. Slides will go up by tomorrow, and you'll be able to catch them there. So Henrik, Etan, Elad, Tomer, everyone from Emza, everyone from Alif, thank you guys so much for an awesome presentation, a fantastic demo, and answering such great questions from the audience. And thank you to the audience for attending today and asking such great questions. And we look forward to seeing you again at another of our AI Tech Talk series. Thank you again, folks from Emza and Alif.
Thank you, Tobias. Thank you for hosting us.
Thank you.